Okay, bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and a very good morning. So insyaAllah, we continue our lecture today with chapter 4. So before that, we recite Surah Al-Fatihah. Amin. Amin, amin, ya rabbal alamin. So for chapter 4 is overhead lines and its mechanical characteristic. Okay, this is the contents of chapter 4, starting with introduction, right? And then the main components of overhead lines. Okay, we have the main components of overhead lines, the conductor materials, the line supports, insulators, corona, sag, and also the mechanical principles. Okay, so we start with the introduction. Okay, so electric power can be transmitted or distributed either by means of underground cables or overhead lines. So as you can see here, this is the example of the overhead lines. Okay, however, the underground cables are rarely used for transmission because of two main reasons, right? The first one is the power is generally transmitted over long distance to the load centers. So therefore, the cost will be very high for installation. Alright. Secondly, electric power has to be transmitted at high voltage for economic reason. Alright. So hence, it is very difficult to provide proper insulation to the cable to withstand the high voltage. Okay. So therefore, as a rule, power transmission over long distance is carried out using the overhead lines. Alright. Okay, next is the main components of overhead lines. Alright, so this is the diagram. Okay, if you can see here, so this is the diagram of the overhead lines. Okay, so an overhead line may be used to transmit or distribute electric power. The successful operation of an overhead line depends to a great extent upon the mechanical design of the line. Okay, so while constructing an overhead line, so it should be ensured that the mechanical strength of the line is such so as to provide against the most probable weather conditions. So in general, the main components of an overhead lines are, okay, the first one is the conductor. Alright, so first is the conductor. So which one is the conductor? So conductor here, okay, this one, number 1, this is the conductor. So conductor, purpose of these conductors is to carry the electric power from the sending end station to the receiving end station. That is the conductors, or we call as the cable, right? Conductors of the cable, right? And then second is the supports, line supports. So this is we call as a line support, which is the poles or towers, and the purpose is to keep the conductors at a suitable level above the ground. Okay, so that one is the number 2. This is the supports. And the third one is the insulators. Okay, which one is the insulator here? Right, so this one, number 3. This is the insulators. So insulators which are attached to supports and insulate the conductors from the ground. Okay, and then fourth, that one is insulators, and then the fourth is the cross arm. So which one is the cross arm? Number 4. Okay, so this one is the cross arm. So cross arm, the purpose is to provide support to the insulators. Okay, you can see here. So it attached with the insulators and also the cable, right? So it will support to the insulators. And then also we have the miscellaneous items such as lightning arresters, phase plates, danger plates, anti-climbing wires, and etc. Okay. So, and then we look on to the conductor materials. What types of materials for conductor? Okay. Okay, the first one, the conductor materials must have high electrical conductivity in order to transmit the electricity from the sending to the receiving. Alright, and then second is high tensile strength in order to withstand the mechanical stress. Third, low cost so that it can be used for long distances. And the fourth is low specific gravity so that the weight per unit volume is small. This is 4 properties of conductor materials that need to be considered. Alright. Okay. So the most commonly used conductor materials for overhead lines are, so the first one is the copper, alright, copper. Second is aluminium. Third is steel cord aluminium. Fourth is galvanized steel, and fifth is the cadmium copper. Okay, we will look on to each of these conductor materials after this. Okay. The choice of a particular material will depend upon the cost, the required electrical and mechanical properties, and also the local conditions. Okay, we go one by one for the conductor materials. The first one is the copper. Okay, copper is an ideal material for overhead lines owing to its high electrical conductivity and also greater tensile strength. Alright. So copper also has higher current density, means that the current carrying capacity of copper per unit of X sectional area is quite large. Alright. So this will lead to 3 advantages. The first one is smaller X sectional area of conductor is required. Okay. Because of it has the high electrical conductivity, therefore the smaller X sectional area just is required. Okay, so because of the smaller X sectional area is required, therefore the area offered by the conductor to wind loads is reduced. Okay, and then this metal is quite homogeneous, durable, and also has high scrap value. Okay. There is hardly any doubt that copper is an ideal material for transmission and distribution of electric power. Okay, however, due to its higher cost and non-availability, it is rarely used for these purposes. So nowadays, the trend is to use aluminium in place of copper. Okay. Okay, next conductor materials is aluminium. Okay. Aluminium is cheap, okay, and light as compared to copper, but it has much smaller conductivity and tensile strength. Okay, so for aluminium is cheap and light if we compare with copper, but it has small conductivity and also small tensile strength. The relative comparison of the two materials is brief below. Okay, the first one, the conductivity of the aluminium is 60% compared to the copper. Okay, the smaller conductivity of aluminium means that for any particular transmission efficiency, the X sectional area of conductor must be larger compared with copper. Okay, and then for the same resistance, the diameter of aluminium conductor is about 1.26 times the diameter of the copper conductor. So the increased section of aluminium expose a greater surface to wind pressure. Okay, because of the increased area of the aluminium, therefore it will expose a greater surface to wind pressure. Therefore, supporting tower must be designed for greater strength. Okay, so this often requires the use of higher towers with consequence of greater set. Okay, and then the specific gravity of aluminium, so normally is around 2.71 gram per cubic centimeter, is lower compared to copper, 8.9 gram per cubic centimeter. Okay. Therefore, an aluminium conductor has almost 1/2 the weight of equivalent copper conductor. For this reason, the supporting structures for aluminium need not be made so strong compared to copper conductor. So, being light, because of this aluminium is light, so aluminium is liable to greater swings, and therefore larger cross arms are required. Okay, and due to lower tensile strength, the higher coefficient of linear expansion of aluminium, the sag is greater in aluminium conductor if we compare with the copper conductor. Okay, so considering the combined properties of course, okay, as we can see, the aluminium is much cheaper, compared to copper. And then the conductivity, the tensile strength, and then the weight, and etc. So aluminium has an edge over copper. So therefore, it is widely used as a conductor material. Alright. So that one is about aluminium. Then we go to the third conductor materials, which is the steel cord aluminium. So due to the low tensile strength, okay, because of the low tensile strength for the aluminium, so therefore aluminium will produce greater sag lah. Alright. So this prohibits their use for larger span and unsuitable for long distance transmission. So in order to increase the tensile strength, the aluminium conductor is reinforced with a core of galvanized steel wires. So as you can see here from this diagram, okay, the steel cord aluminium conductor consists of central core is the steel, is the galvanized steel, and then it's surrounded by the numbers of aluminium strands. Okay. So this composite conductor is known as the steel conductor aluminium and is abbreviated as the ACSR, aluminium conductor steel reinforced. And usually diameter of both steel, okay, diameter of steel and also the diameter of the steel and also aluminium is same. Okay. The advantages of this steel cord aluminium. So the reinforcement with steel increase, okay, it will increase the tensile strength, but at the same time, it will keep the composite conductor light because of what? It is still surrounded with the aluminium, only the core we replace with the steel. Alright, so therefore steel cord aluminium conductors will produce smaller sag and hence longer span can be used. And due to small sag with steel cord aluminium conductors, towers of smaller height can be used for the steel cord aluminium conductors. And then the fourth is the galvanized steel. So steel has very high tensile strength. So galvanized steel conductor can be used for extremely long spans or for short line sections exposed to abnormally high stresses due to climatic conditions. Alright. So they have been found very suitable in rural areas where cheapness is the main consideration. So due to the poor conductivity and also high resistance of steel, such conductors are not suitable for transmitting large power over a long distance. Okay, alright. And then the final one is the cadmium steel. The conductor material now being employed in certain cases is copper alloyed with the cadmium. Alright, cadmium. With additional of 1% and 2% of cadmium to copper, it will increase the tensile strength by 50%, but the conductivity will be reduced around by 15%. Therefore, cadmium copper conductor can be useful for exceptionally long spans. So, however, due to high cost of cadmium, such conductors will be economically only used for lines of small X section. For example, where the cost of conductor material is comparatively small compared with the cost of supports. Alright. Okay, next is the line supports. Alright. Okay, line supports is the supporting structures for overhead line conductors such as poles and also towers. So in general, the line support should have the following properties. Okay, the first one is high mechanical strength to withstand the weight of conductors and wind loads. Second, the line support should light in weight without loss of mechanical strength. And then cheap in cost and economical to maintain. And finally, longer life and easy accessibility of conductors for maintenance. Right? So the line supports used for transmission and distribution of electric power are of various types, including wooden poles, okay, and then we have the steel poles, the reinforced concrete poles or RCC, and also lattice steel towers. So the choice of supporting structure for a particular case depends upon the line span, the X-sectional area, line voltage, cost, and also the local condition. Right? So we look on to one by one for the line support. The first one is the wooden pole. So these wooden poles are made of seasoned wood and suitable for lines of moderate X-sectional area and of relatively shorter spans. Alright, say up to 50 meters. Okay, this is suitable for the wooden poles. Alright. So such supports are cheap. Okay, it is cheap and easily available, provide insulating properties, and therefore are widely used for distribution purposes in rural areas as an economical proposition. Alright. However, these wooden poles have some disadvantages, which are it is tendency to rot below the ground level. Okay, below the ground level, and then it has a smaller lifespan, around 20 to 25 years. So these wooden supports also cannot be used for voltages higher than 20 kilovolt. It has a less mechanical strength and require periodical inspection. So this is the diagram of an example of the wooden poles. Okay. So next is the steel pole. So the steel poles are often used as a substitute for the wooden poles. They possess greater mechanical strength, okay, greater mechanical strength, longer life, and permit longer spans to be used. So such poles are generally used for distribution purposes in the cities. Alright. So this type of supports need to be galvanized or painted in order to prolong its life. Okay. So this is the diagram. This is the picture of the steel pole. Okay. Third is the reinforced concrete poles or RCC. So the reinforced concrete posts have become very popular as line supports in recent years. Okay, they have greater mechanical strength, okay, longer life, and permit longer spans than steel poles. Moreover, they give good outlook, require little maintenance, and have good insulating properties. Okay, so these figures shows the RCC poles for single circuit, and then these figures shows the RCC poles for double circuit. So the main difficulty with the use of this pole is the high cost of transports owing to their heavy weight. Therefore, such poles are often manufactured at the site in order to avoid heavy cost of transportation. Okay. And then the fourth line support is the lattice steel towers. So in practice, wooden, steel and reinforced concrete posts are used for distribution purposes at low voltage, say up to 11 kV. So however, for long distance transmission at higher voltage, steel towers are invariably employed. Okay, so these steel towers have greater mechanical strength, it has longer life, and can withstand more severe climatic conditions and permits the use of the longer spans. Okay, the risk of interrupted service due to broken or punctured insulation is considerably reduced owing to longer spans. And then tower footings are usually grounded by driving roads into the earth, and this minimize the lightning trouble as each tower acts as a lightning conductor because it has grounded rods in this line support. So this is the figure of the lattice steel towers, right? Okay, next is the cross arm. So cross arm is purposely, okay, this is the cross arm. So this cross arm is purposely to hold the insulators. Okay, this one is the insulators, and then we have the conductors. Alright, so this cross arm is purposely to hold the insulators and also the conductors. Alright, so this is one of the line support. Okay, next is the insulators. Alright, so the overhead line conductors should be supported on the poles or towers in such a way that currents from conductors do not flow to earth through supports. Alright, therefore means that the line conductors must be properly insulated from supports. So this is achieved by securing line conductors to supports with the help of insulators. That is the purpose of the insulators. So the insulators provide necessary insulation between the line conductors and tower or poles, thus prevent any leakage current from conductors to the earth. Okay, so insulator is very important in the overhead lines. Alright, so this is this is the figure of the insulators as we can see here. So it holds the conductors, and then the cross arm will hold the insulators. Okay, so in general, the insulators should have the following desirable properties. Okay, so the first one is insulators must have high mechanical strength to withstand the conductor loads, okay, and then wind loads and also etc. Second properties is insulator must have high electrical resistance of insulator material in order to avoid the leakage currents to the earth. And then high relative permittivity. So permittivity What is permittivity? Is the ability of a material to store energy in electric field. Okay, so this insulator must have a high relative permittivity in order that the dielectric strength is high. So what is dielectric strength? So dielectric is the maximum electric field that a pure material can withstand under either conditions without breaking down. Okay, that is called as a dielectric strength. So these insulators must have high relative permittivity and also high dielectric strength. Okay, so the insulator material should be non-porous, free from impurities, means that it must be clean, and cracks. Okay, otherwise the permittivity is lowered. Okay, and then the most commonly used material for insulators of overhead line is porcelain. Okay, basically for materials that commonly used is porcelain, but glass, statite, and special composition materials are also used to a limited extent. Okay, so why porcelain is used? It is because porcelain is stronger mechanically compared to glass. So it gives less trouble from leakage current and is less affected by changes of temperature. Okay. So there's 4 types of insulators. So first one, okay, so the successful operation of an overhead line depends to a considerable extent upon the proper selection of insulators. Okay, there are several types of insulators, but the most commonly used are we have the pin type insulators, the suspension type insulators, the strain insulators, and also the shackle insulator. Okay, so we look on to one by one for the insulators. The first one is the pin type insulator. Okay, this figure shows the pin type of insulator. Okay, this one. So the pin type insulators, as the name suggests, the pin type insulator is secured to the cross arm on the pole. So there is a groove on the upper end of the insulator for housing the conductor. So pin type insulators are used for transmission and distribution of electric power at voltages up to 33 kV. Okay, so beyond operating voltage of 33 kV, the pin type insulators become too bulky and hence uneconomical. So if less than 33 kV, then we can use the pin type insulator. Okay. Next is the suspension type insulator. Okay, the cost of pin type insulator increases rapidly as the working voltage is increased. Therefore, this type of insulator is not economical beyond 33 kV. For high voltages, means that more than 33 kV, it is usually in practice to use this type of suspension type insulators. Okay, so this is the figure of the suspension type insulators. You can see here. All right. So they consist of a number of porcelain discs connected in series by metal links in the form of a string. Okay, you can see here there's a number of porcelain that connected in series lah. Okay, the conductor is suspended at the bottom end of this string while other end is secured to the cross arm of the tower. So this is the cross arm of the tower and the bottom of this string will be suspended to the conductor, to the cable. Okay, the number of these is in series would obviously depend on the working voltage. So each unit of this is designed for low voltage. For example, say 11 kV. Okay, so if the working voltage is 66 kV, so then 6 discs will be provided on the string. So it depends on the working voltage for the number of the discs in series. Alright. So this is the advantages of these suspension type insulators. So suspension type insulators are cheaper than pin type of insulators for voltages beyond 33 kV. Okay, so it's cheaper. And then each unit or disc of suspension types is designed for low voltage, usually 11 kV. So depending on the working voltage, the desired number of discs can be connected in series. Okay. So if any one of these discs is damaged, the whole string does not become useless because the damaged disc can be replaced. Okay, for example, if we have 6 discs, and for example, one disc is damaged, so we can just replace. We can just took out the damaged disc. We can replace with the new disc without effect to the whole string of the suspension insulators. Alright. So the suspension arrangement provides greater flexibility to the line. Okay. So the connection at the cross arm is such that insulator string is free to swing in any direction and can take up the position where mechanical stresses are minimum. Okay. Okay, third is the string insulators. So when there is a dead end of the line, okay, or there is a corner or sharp curve, the line is subjected to greater tension. So in order to relieve the line of excessive tension, string insulators are used. This is type of, okay, so you can see here, this is the figure of the string insulators. Alright. The fourth is the shackle insulator. So in early days, the shackle insulators were used as string insulators. But nowadays, they are frequently used for low voltage distribution lines. Such insulators can be used either in a horizontal position or in a vertical position. Right? So this one is the vertical position. Okay. So they can be directly fixed to the pole with a bolt or to the cross arm. So this is the figure of the shackle insulator fixed to the pole. Okay. Okay. Next, we look on to the potential distribution over suspension insulator string. A string of suspension insulators consists of a number of porcelain discs connected in series through metallic links. So if you refer to this figure, so we have three porcelain discs that connected in series 1, 2, 3. Okay. So the porcelain portion of each disc is in between two metallics. So if we look here, this is the porcelain disc, and then we have two metal links here. Alright. So because of this connection, so each disc will form a capacitor C. Okay. So because of this, we have two metal links. Okay, two metal links and also one insulators. So it will act as a capacitance. Alright. So this is known as the mutual capacitance. Mutual or the self-capacitance. So capacitance is the ability of a body to store an electric charge. So if there is a mutual capacitance alone, so if there's only mutual capacitance, so the current, the charging current will be the same through all the discs. So if you look here, because of this is a series electrical circuit, okay, so the charging current is the same, I1, I2 and also I3. So because of it's in series and the capacitance is same, so I1 equals to I2 equals to I3. Alright. So consequently, the voltage across each unit would be also the same. So because of I1 equals to I2 equals to I3, so V1 equals to V2 equals to V3. Alright. So V total is V1 plus V2 plus V3. So V total is divided by 3 for the voltage across of all the insulators. Alright. So in actual practice, capacitance also exists between metals. So if we can see here, so we have here is the cross arm, for example, and then we have the tower here. So in actual practice, capacitance also will be exist between the metal fitting of each disc, okay, each disc, and also the tower of the earth. Okay, so here, so because of we have the connection between the metal fitting of the disc and also the tower of the earth, therefore it will exist the capacitance as we call as the shunt capacitance C1. Okay. Alright, so due to the shunt capacitance, the charging current is not the same. Okay, if you look here, so once the current, there is a mutual capacitance, so the charging current is not the same through all these of the string. For example, we have I here, so I becomes I3 plus I3, capital I3. So I1 is not same as I2 and not same as I3. Okay, so therefore the voltage across the each disc will also different. So now V1 is not same as V2, is not same as V3. Okay, and then the disc nearest to the line conductor, okay, this one V3. V3 is the disc is the voltage that nearest to the line conductor will have the maximum voltage. Okay, V3 will have the maximum voltage. Alright, because the charging current through the string has the maximum value at the disc near to the conductor. Okay, because of this I is also the maximum current because it is allocated at nearest to the conductor, and after this it will connect to the conductor. So the charging current is high here, therefore the voltage, the V3, the voltage near to the line conductor also high. So thus referring to the figure 3, okay, this one is figure 3. Alright, V3 is much bigger than V2 or V1. Okay, so V3 is the maximum voltage. Okay, so the following points may be noted regarding the potential distribution over a string of suspension insulators, which are: the first one, the voltage is not distributed uniformly across the individual discs due to the presence of the shunt capacitance. Okay, second, the disc nearest to the conductor has the maximum voltage across it. So V3 is the V max. Alright. As we move towards the cross arm, okay, the voltage across each disc is reducing. Means that V3 is bigger than V2 is bigger than V1. The unit nearest to the conductor is under maximum electrical stress and is likely to be punctured. Okay, if the voltage across the string were DC, then the voltage across each unit will be the same. It is because insulator capacitance are ineffective for DC. So if this system is DC, So all the voltage across each unit will be same lah, because these insulator capacitance are not effective for DC voltage. Alright. And then next we look on to the string efficiency. The voltage applied across the string of suspension insulators is not uniformly distributed across various discs. Alright, so the disc nearest to the conductor has much higher potential compared to the other discs. So this unequal potential distribution is undesirable and is usually expressed in terms of the string efficiency. So we can calculate the string efficiency by using this equation. Okay, so voltage across the string. Okay, this one is VT, the total voltage across the string. You divide it with the N. N is the number of discs in the string. For example, for this case, we have 3 insulators. So here is 3 lah. Okay, if you have 6 insulators, so 6. You times with the voltage across this nearest to the conductor, which is the V maximum. Then you can get the efficiency of the string. Okay. So string efficiency is an important consideration since it decides the potential distribution along the string. Okay. The greater the string efficiency, the more uniform is the voltage distribution. Okay. So thus 100% strength efficiency is an ideal case for which the voltage across the each disc will be exactly the same. Okay. If you got V1 equals to V2 equals to V3, then you will get the string efficiency is 100%. Okay. Now we look on to the mathematical expression for the string efficiency. So let us suppose that self-capacitance of each disc is C. Okay. So this is the mutual capacitance of self-capacitance is C. So assume that shunt capacitance, the C1, is some fraction K of self-capacitance, which is C1 is equal to Kc. Starting from the cross arm or tower, the voltage across each unit is V1. Okay, this one is cross arm, as we know, cross arm. And then here is the tower. Okay, we start with the cross arm. So the first one is V1, second is V2, and third is V3. Okay. Okay, in order to find the string efficiency, first we have to draw this circuit, right? So from this circuit, we have to apply the Kirchhoff currents law. Okay, we have 3 nodes here, A, B, and C. So we start first with node A. Okay, as we know that the Kirchhoff currents law, the ingoing current, okay, ingoing current will equivalent to outgoing current, right? Right. So from this node, we can see here I2, the ingoing current, which is the I2, right? I2 equivalent to the outgoing current. Outgoing current, we have 2 I1, capital I1 plus small I1. Alright, this one, and this one. Okay, so here is the equation. Okay, and then for I2, we have to write as the equation for I2 is I2 equivalent to V2 omega C. So how we get this equation? Alright, so as we know that V equivalents to IR. Okay, so R is the resistance, but in this case we don't have the resistance. What we have here is the capacitance reactance, which is XC. Okay, so we have to replace XC with R, so V equivalent to IXC. Okay, so as we know that XC equivalent to 1 over omega C. Okay, so we replace this equation into this equation, so we get V equivalent to I over omega C. So that's why we can get I equivalent to V omega C. That's why we got here I2 equal to V2 omega C. Okay, this one. I2 is V2 divided by omega C. Okay, and then the outgoing current is capital I1, so this one, so V1 omega C plus with small I1, so this one is small I1, so V1, okay, the voltage here is V1 times with omega C1, okay. And then we have to replace, as I mentioned before, C1 is equivalent to KC, right? So you have to replace, substitute this C1, so it will give this equation. Okay, so V2 omega C equivalent to V1 omega C plus V1 omega KC. So we don't have now the C1 here in this equation. So and then okay, then we simplify this equation and then we get this equation V2 equivalent to V1 1 plus K. Okay, and then that one we have settled with node A. Okay, node A. Then we have to do for node B. Okay, so we have to apply the Kirchhoff current law for node B as well. Okay, so we look on to node B. Okay. Okay, now we do the apply the Kirchhoff current law at node B. Okay, so we look on to this node. Okay, node B. So node B we have I3 here. Okay, I3 equivalent to the outgoing is capital I2 plus small I2 here. Okay, it's not. Okay, so we have to do the next equation is I3 equivalent to V3 omega C, and then you have to come up with I2. What is the equation for I2? I2 is capital I2 is V2 omega C, and then plus small I2. Okay, for this small I2 is we have to consider the voltage, the potential is from this node until node B, means that the voltage is now V1 plus V2. Okay, so V1 plus V2, so the voltage for small I2 is V1 plus V2. Okay, so V1 plus V2 times with omega C1. Alright, that one is for the small I2. Okay, and then we simplify the equation. Then we can get, okay, the second is this one lah. We just replace C1 equivalent to KC. Then you simplify more the equation to be V3 equivalent to, is that we can just cancel out this, okay, and then we get V3 equivalent to V2 plus V1 plus V2K. Okay, and then we try to simplify until we get V3 equivalent to V1 1 times 1 plus 3K plus K squared. Alright, so this is the equation for V2, and then this is the equation for V3. Okay, next So now from here, we can get the total voltage, the total voltage from the conductor and the tower. From here, this one is the tower, which is, or the earth, until to the conductor. So this one is the conductor. Okay, conductor, right? Okay. So V is the V total. So V total is V1. You have to plus with V2 and also V3. Okay. So you got the V total. And then you refer to the previous equation. You just insert V2, what is for the equation for V2 and also V3. Then you simplify, you will get V equivalent to V1, 1 plus K times 3 plus K. Okay. So V1 is here. Okay. And then V2 is this one. And then V3 is this one. Okay. So we write back. Okay. So this one is V2 equivalent to V1, 1 plus K. Okay. And then second is V3. Okay, V3 equivalent to V1, 1 plus 3K plus K squared. Alright. And then the third one is V equivalent to V1, 1 plus K, 3 plus K. Okay. So at last we will get this one. Okay. So from this 1, 2 and 3, we get V1 equivalent to V2 over 1 plus K equivalent to V3 1 plus 3K plus K squared equivalent to V over 1 plus K times 3 plus K. Okay. This one lah. Alright. Okay. Then from here, okay, we can know that the voltage across the top unit, which is the V1, this one, is the equivalent to V total, this one lah, divide by 1 plus K times 3 plus K. Okay. So that one is the voltage across top unit. Okay. So if you want to find the voltage across second unit from the top, so you can get V2 equivalent to V1 times 1 plus K. Okay, this one. This one lah. Okay. And then if you want to find the voltage across third unit from the top, so you can get V3 equivalent to V1, this one, V1, 1 plus 3K plus K squared. Okay. And then after that, we can calculate the string efficiency. So the string efficiency is Okay, that's it. So this one is then we can calculate the string efficiency. So the string efficiency is the voltage across the string, which is the VT, V total. Okay, V total is V1 plus V2 plus V3. Then you divide by n. N is the number of the string. Okay, we have 3 string here. Okay, we have 3 numbers of insulators. So n is the number of the insulators. So we have 3 insulators here. So that's why we write here 3 and times with the voltage across this nearest to the conductor. So V3 is the voltage across this nearest to the conductor, which is the Vmax. So here is the V3. Then you times with 100%. Then you can get the percentage of the string efficiency. Okay. It's okay. Okay. After this, we go to example to enhance your understanding regarding this string efficiency. Right? As I mentioned before, right? This is the equation to get the voltage across second unit from top, which is V2, and also the Vmax V3. Okay, this is the equation. Okay, you can just get the equation. Okay, so in order to get this equation, you have to do the derivation lah. Derivation from the circuit. Okay. So next is the method of improving string efficiency. So it has been seen that the potential distribution in a string of suspension insulators is not uniform. As I mentioned before, that the voltage at V3 is bigger than V2 and bigger than V1, right? So the potential distribution is not uniform. Okay. So the maximum voltage appears across the insulator nearest to the line conductor. Okay, as we know here, this is the Vmax. Okay, the highest voltage, okay, the maximum voltage here, and then it will decreases progressively as the cross arm is approached. So you can see here now we have the cross arm, so it will decrease progressively. Okay, here from V3 to V1. Okay, so if the insulation of the highest stress insulator, which is the nearest to the conductor, breakdowns or flashover takes place, the breakdown of other units will take place in succession. Okay, so this necessitates to equalize the potential across the various units of the string, which is to improve the string efficiency. So one of the methods for this purpose, which is to improve the string efficiency, is by using the longer cross arm. Okay, the value of string efficiency, okay, depends upon the value of K. So as we know that K is the ratio of the shunt capacitance over the mutual or self-capacitance. Okay. So this one is the shunt capacitance, which is the C1, and this one is the mutual capacitance or self-capacitance, which is the C. Alright. So the string efficiency depends on the K. So the lesser the value of K, the greater is the string efficiency. And more uniform is the voltage distribution. Okay, so how we want to decrease the value of K? So by reducing the shunt capacitance, the C1. So we have to reduce the shunt capacitance in order to reduce the K and to increase the efficiency of the string. Okay. So, in order to reduce the shunt capacitance, we have to increase the distance of the conductor from the tower. This one. Okay. So, we have to increase the distance of the conductor to the tower, which is we have to increase we have to longer the cross arm in order to reduce the value of the shunt capacitance. Okay. However, limitations of the cost and also strength of the tower do not allow the use of very long cross arms. Okay. And in practice, K equivalent to 0.1 is the limit that can be achieved. Alright. Okay, while solving problems relating to the string efficiency, the following points must be kept in mind. Okay, the first one is the maximum voltage appears across the disc nearest to the conductor. So this one must be the highest value of the voltage, the Vmax. So if you calculate, okay, if you do some example tutorial and then you get the V here, the voltage here is not the highest value, then it is wrong. Okay, so you must make sure that the maximum voltage is at this point near to the conductor. Alright, and then the second one is the voltage across the string, okay, which is the VT. Okay, here VT is equal to phase voltage, okay, which is the voltage across the string is voltage between the line, this one is the line, and the earth. Alright, so it is a phase voltage, so VT is the V phase. Alright, and then if in the example or questions you get the line voltage, then you have to change from line voltage to the phase voltage. So this is the equation in order to calculate the V phase. For example, we have here V line equivalent to Z3 V phase, right? So if we want to calculate the V phase, then we get V line over V over Z3. Okay. Okay, now we look on to the example 4.1. So in a 33 kV overhead line, so 33 kV is referring to the line voltage. So there are 3 units in the string of insulators, means that N equivalent to 3. So if the capacitance between each insulator pin and earth is 11% of self-capacitance of each insulator, this one means that C1 equivalent to KC, alright. So K is 11% of the self-capacitance, so means that K equivalent to 0.11. Okay, so you have to find first is the distribution of voltage over 3 insulators, means that the total voltage VT, and then the second one is the string efficiency. Okay, so this is the solution for example 4.1. First, you have to draw the equivalent circuit. This is the equivalent circuit for this question. So you can see here we have 3 insulators. So you have to draw 3 insulators lah capacitance. So if the questions mention 4, then you have to draw 4 capacitance. And then the second things is you have to calculate what is the voltage across the string, which is the VT. Okay, and then third is determine the K equivalent to shunt capacitance over self capacitance. As I mentioned before, K is equivalent to 0.11. Okay, and then you have to apply the Kirchhoff current law at node E and B. Then you'll get the string efficiency. Okay, so I will show you in details on how to calculate, how to solve this example 4.1. Okay, so first, as I mentioned before, you have to draw the circuit of the system. Okay, and then second is you have to find what is the voltage lah. Alright, so for the VT, so in this question it states that the voltage line VL equivalent to 33 kV, right? So as we know that the voltage across the string, which is the phase voltage, is V line over cert 3. So 33 kV you divide by cert 3, then you get 19.05 kV. Okay, so this one is the V phase or the V total, the voltage distribution for this system. Okay, voltage across the string. Okay, and then we know that K equivalent to C1 over C. So in here we get 0.11 from the equation, from the question. Okay, from the question we get that K equivalent to 0.11. Okay, and then you have to do the KCL at node A. Okay, we start with the KCL at node A. Okay, so at node A, you have to write here node A. Okay, so this is the node A. Okay, so I2 equivalent to capital I1 plus small I1. Okay, so V2 omega C is equal to V1 omega C plus V1K omega C. So here we can just cancel out. Okay, right, then we get V2 equivalent to V1 1 plus K. Alright, okay, so here we have V1 1 plus 0.11. So we got V2 equivalent to 1.11 V1. Okay, so this is the first equation for node A. Okay, then you have to do the KCL at node B. So next is node B. Okay, node B. Which one is node B? Yeah, here is node B. So I3 equivalent to capital I2 plus small I2. Okay, so V3 omega C equivalent to V2 omega C plus V1 plus V2 K omega C. Okay, so we just cancel out this one. Okay, then we get V3 equivalent to V2 plus V1 plus V2K. So this one, we look on the previous equation. So V2 equivalent to 1.11 V1 plus V1 plus 1.11 V1 times with 0.11. Okay, then we get V3 equivalent to 1.342 V1. Okay, so we have V2 and also the equation for V3, right? Okay. Then, so you got here for number 1. So voltage across the whole string. So we have known that Vt equivalent to V1 plus V2 plus V3. Okay. So we know that from the previous equation, V1 is V1 plus V2 is 1.11 V1 plus V3 is 1.342 V1. Okay. So we get here is 3.45 to V1. Okay. So we know from previous Vt is equivalent to 19.05 kilovolt. Okay. So kilovolt. So equivalent to 3.452 V1 kilovolt. Okay. So now you have to calculate what is the voltage across top unit. Okay, top unit, which is this one. What is V1? Okay, so this one is V1. So from this equation, okay, then you'll get 19.05 K. You divide by 3.452 K. Then you get V1 is 5.52 kV. So this one is V1. Okay. The top unit, the voltage across the top unit. Okay. That one is the V1. Now we calculate for V2. Okay. So voltage across the middle unit, okay, or V2. So V2 is, from the previous equation, is 1.11 V1. Okay. So you just times V2 equivalent to 1.11 times V1, which is 5.52 K. You'll get 6.13 kV. Okay. Okay, then you can calculate what is the maximum voltage of V across bottom unit. Okay. Okay, V3 equivalent to 1.342 V1. Okay. So you just times, this one is Vt, which is the Vmax. You calculate 1.342 K, you times with V1. Okay, sorry, this one is not K. Okay, so this times with 5.52 K, then you get 7.4 kilowatt. Okay, so you can see lah, V3 is larger, is bigger than V2. V2 is bigger than V1. Okay, so that one is how we want to get the voltage across the string. Okay. Okay, and then we have to calculate what is the string efficiency, right? Okay, then we have to calculate what is the string efficiency. The string efficiency, which is okay. Alright, so as we know that the equation for this string efficiency is V across the string, which is the VT, you divide by number of isolators, you times with Vmax. Alright, and times with 100% lah. So in this case, VT is 19.05. Okay, and then you divide it by 3 times with Vmax. Vmax is 7.4K. You times with 100%. Then you get 85.8%. Okay, so this is the answer for the string efficiency for the example 4.1. Alright. Okay, next we go to example 4.2. A 3-phase transmission line is being supported by 3 disc insulators, means that N equivalent to 3. Okay, same with the previous example. The potentials across top unit, which is near to the tower, and middle unit is 8 kV and 11 kV respectively, means that 8 kV is V1 and 11 kV is V2. Alright, V2. Okay, so calculate the ratio of the capacitance between pin and earth to the self-capacitance of each unit, means that you have to calculate what is K, and then the line voltage, okay, V line, and also the string efficiency. Okay, so this is the solution for example 4.2. So first you have to draw the circuit. Okay, so the equivalent circuit of string insulators is the same as the previous figure lah, because we have three insulators, right? So, and that is given that V1 is 8 kV and V2 is 11 kV. So first we have to find what is K. So let K be the ratio of capacitance between pin and earth to self-capacitance lah. So this one is K equivalent to C1 over C. So if C farad is the self-capacitance of each unit, then capacitance between pin and earth is equivalent to Kc, means that the mutual capacitance is equivalent to K times C. Okay. So first we have to apply the KCL to the node A or junction A. So this is the equation for the KCL, and then you derive here, then you simplify the equation and get V2 equivalent to V1 1 plus K. Alright, so this one means that, okay, alright, so this one from here V2 equivalent to V1 plus K V1, right? Okay, so K V1 equivalent to V2 minus V1. Okay, V1. Okay, So K equivalent to V2 minus V1, you divide by V1. Okay, so this one is here. So that's why we just substitute the value here inside this equation. So V2 is 11, V1 is 8, and V1 is 8. So we get K equivalent to 0.375. Alright. And then next is we want to calculate what is the line voltage. So we have to apply the KCL to the B, not B, or the junction B. So this is the KCL equation. Alright, and then we simplify the equation. We'll get this one lah, V3 equivalent to V2 plus V1 plus V2K. So we just substitute all the values inside here. Okay, then we get this is the value for V3. Okay, so V3, and then we can get what is the voltage between line and earth. Means that VT, the total voltage. Okay, line and earth. So this one we call as a VT. Okay, alright, VT. So VT is V1 plus V2 bus plus V3. So V1 is 8, V2 is 11, V3 is 18.12. Then we get VT is equivalent to 37.12 kilovolt. But this one is in phase voltage, V phase. Alright. So we have to change it to line voltage. So by equation, this one, Z3 times VP, V phase. Then we can get the V line. Alright. So Z3 times VP, VP is 37.12 kV. Then we get the line voltage is 64.2828 kV. Alright. And then finally we can find what is the string efficiency. The string efficiency is the voltage across the string, which is the VT. Okay, the total voltage. And then you divide by number of insulators, which is 3. And then you times with the Vmax, V3. Alright. So you get 68.28% for the string efficiency for this case. Alright. Okay, next is the corona. Okay, what is corona? So basically, if we have two conductors, alright, this one is 1, 2, alright, and have the spacing here. Okay, spacing, and have the diameters. Okay, diameters of the conductors. So if when an alternating potential difference is applied across these two conductors whose spacing is large as compared to their diameters, okay, there is no apparent change in the condition of atmospheric air surrounding the wires if the applied voltage is low. Alright. However, when the applied voltage exceeds a certain value called critical disruptive voltage, the conductors are surrounded by a faint violet glow called corona. So if the applied voltage exceeds a certain value, so corona will be happen. Right? So phenomenon of violet glow, hissing noise, and production of ozone gas in an overhead transmission line is known as corona. Right? Corona are caused when air around an energized conductors get ionized, causing a discharge. Alright. So the phenomenon of corona is affected by the physical state of the atmosphere as well as by the conditions of the line. So the following are the factors upon which corona depends. Okay. So we have four factors affecting corona. The first one is atmosphere. Okay, atmosphere. As corona is formed due to ionization of air surrounding the conductors, therefore it is affected by the physical state of atmosphere. In the stormy weather, the number of ions is more than normal, and as such, corona occurs at much less voltage as compared with fair weather. Alright. Second one is the conductor size. Okay. The corona effect depends upon the shape and conditions of the conductors. The rough and irregular surface will give rise to more corona because unevenness of the surface decreases the value of breakdown voltage. Thus, a stranded conductor has irregular surface and hence gives rise to more corona compared to the solid conductor. Okay, third one is the spacing between the conductors. If the spacing between the conductors is made very large as compared to their diameters, there may not be any corona effect. Okay, because of what? Because larger distance between conductors reduce the electrostatic stresses at the conductor surface, thus avoiding corona formation. Okay, and finally is the line voltage. The line voltage greatly affects corona. If it is low, there is no change in the condition of air surrounding the conductors and hence no corona is formed. However, if the line voltage has such a value that electrostatic stresses develop at the conductor surface make the air around the conductor conducting, then corona is formed. Alright, that is 4 factors affecting corona. Okay, corona has many advantages and disadvantages. So in the correct design of a high voltage overhead line, a balance should be struck between the advantages and also disadvantages. Okay, first we look on to the advantages of the corona. So the first one is due to the corona formation, alright, the air surrounding becomes conducting, okay, and virtual diameter of the conductor is increased. So the increased diameter will reduce the electrostatic stress between the conductors, right? And then corona also reduce the effects of transients produced by the surge. Okay, however, the disadvantages of the corona, so corona is accompanied by a loss of energy. So this will affect the transmission efficiency of the line. And then ozone is produced by corona and may cause corrosion of the conductor due to the chemical action. And also the current drawn by the line due to corona, okay, the current drawn by the line due to corona is non-sinusoidal, and hence non-sinusoidal voltage drop occurs in the line, and this may cause interference with neighboring communication lines. This is all the advantages and also the disadvantages of corona. Okay. So how we want to reduce the corona effect? So methods to reduce the corona effect are 2. The first one is by increasing the conductor size. So by increasing the conductor size, the voltage at which corona occurs is raised, and hence corona effects are considerably reduced. Alright. This is one of the reasons that ACSR conductors, which have a larger cross-sectional area, are used in transmission lines. Alright. Okay, next one, second, is by increasing the conductor spacing. By increasing the spacing between conductors, the voltage at which corona occurs is raised, and hence corona effects can be eliminated. So, however, spacing cannot be increased too much, otherwise, the cost of supporting structure, for example, bigger cross arms and also supports, may increase to a considerable extent. Okay. So next is the set. So sag in overhead lines, sag S can be defined as the difference in level between points of support. So you can see here, so we have two supports here, A and also B. And then we have the lowest point on the conductor is 0. So this one we call as sag S. Alright. Okay. So while erecting an overhead line, it is very important that conductors are under safe tension. Right. So if the conductors are too much stretched between supports, okay, between these supports, okay, in a bid to save conductor material, the stress in the conductor may reach unsafe value, and in certain cases, the conductor may break due to excessive tension. Okay, so in order to permit safe tension in the conductors, they are not fully stretched, but are allowed to have a dip or sag. Ni lah, this one Alright, so in Malay, dia kelendutan lah. Sag is kelendutan. Okay, dia tak tegang but have a kelendutan tu lah. Alright. Okay, so the sag should be adjusted so that the tension in the conductors is within safe limits. Okay, here is the figure. You can see here we have two towers, right? Two towers and also conductors. Okay, so if you look at the first one, this one, the upper level, okay, this is the sag of conductor during the cold day. And then the lower level, you can see that this is the sag of the conductor during hot day, which is the maximum sag full load. Alright. Okay. So in an overhead line, the sag should be so adjusted that the tension in the conductors is within safe limit. So the tension is governed by conductor weight, effect of wind, ice loading and temperature variations. So it is a standard practice to keep conductor tension less than 50% of the ultimate tensile strength. Okay, and then the sag can be calculated using two cases. Okay, the first one is when supports are equal levels, and the second one is when the supports are at unequal levels. Alright, so if you look on this figure, the support is at equal levels. So we look one by one. The first one is when the supports are at equal levels. So A and B are at equal levels. Okay, so we can see here there's a conductor between two equal level supports A and B. Okay, and also 0 here, and also 0 as the lowest point. So when supports are at equal levels, so we can use this equation to calculate the sag. Okay, so sag is the W times L squared divided by 8T, where W is the weight per unit length of conductor, units is kilogram per meter, and then you times with the length of the span, and then you divide by 8 times T, which is the tension in the conductor. Okay, and then tension in the conductor T is equivalent to ultimate strength divided by safety factor. Okay, we look on to the example 4.3. A 132 kV transmission line has the following data. First one is the weight of the conductor is 630. The weight of the conductor is 680 kilogram per kilometer. So this one is W. And then the length of the span, okay, equivalent to 260 meters. So this is L. And then we have ultimate strength is 3,100 kilogram and safety factor 2. So if the ground clearance required is 10 meters, so ground clearance is 10 meters, right? So find the height above ground at which the conductor should be supported. Means that we have to find here lah, the height lah, alright? So here we know the ground clearance, so we have to find what is the sag, then we can get the height. Alright, this is the solution for example 4.3. First, you have to calculate what is the weight of conductor per meters. Okay, so before in the questions, it gives that kilogram per kilometer. So we have to change to kilogram per meter. Okay. So for the weight of conductor per meter run, so W is equal to 680 divided by 1000. 1000 because of what? We know that refer to the questions. The weight of conductor is 680 kilogram per kilometer, right? So 1 kilometer equals to 1000 meters. So we want to change from kilogram per kilometers to kilogram per meter. So the weight must be divided by 1000, which is we get 0.68 kilogram per meter. Alright. So the working tension is T equivalent to ultimate strength divided by safety factor. So the ultimate strength is 3100 divided by 2. So we get 1550 kilogram. Okay. And then the span length L is 260 meters. So by using this equation, we will get the sag for this system is 3.7 meters. Okay. So this is the sag. Alright. As we know from the questions, it says that the ground clearance is 10 meters. Okay. So here is 10 meters. Then we can get the value of H. Okay. Which is the conductor should be supported at the height of H equals to ground clearance plus with the sag, which is 10 meters plus 3.7. So you get 13.7 meters. Alright. So next is the case when the supports are at unequal levels. You can see lah from this figure, A and B is not equal levels. Okay. So if not equal levels, so we have to calculate two sag lah. The first one is the first sag. Okay, this one from A to 0. So this one we call as the first sag, right? Okay. And then for point B, we have the second sag from B to 0 is the second sag. So this one is the sag 2. Alright. Okay. So for sag 1, so the equation we can use the first one and the second one in order to get the value for sag 1 and sag 2. Alright. So we look on to the example 4.4. So the towers of height 30 meters. So the first one A is 30 meters and the second one B is 90 meters respectively support a transmission line conductor at water crossing. The horizontal distances between the towers in 500 meters, which is the span. Okay, so span is the span between the towers is 500 meters. So if the tension in the conductor is 1600 kg, find the minimum clearance of the conductor and water and clearance midway between the supports. So weight of conductor is 1.5 kilogram per meter. Bases of the towers can be considered to be at water level. Okay, this is the solution for 4.4. Alright. So first you have to draw this diagram. Okay. Depends on the question. Alright. So in this question, the tower is not equal, which is the A and also B. And then you have to find what is the minimum clearance of the conductor and water, which means this one. Alright. So this one, H1. And also you have to find the clearance midway between the supports. So P is the midway, so you have to find H2. Okay. Alright. So first, you know that the span between the tower A and B is 500, right? Okay, this one L. So x1 you plus with x2, then you get 500 meters. So this is the first equation. Okay, and then the weight of the conductors is 1.5 kilograms per meter, and the tension is 1600 kilogram. Okay, so here you can get the height, the difference height between A and B is here. Okay, H is, as we know here, the height of tower B is 90 meters. Right, this one is 90. And then the height for tower A is 30 meters. Right, so the difference between tower A and also tower B, so we get H. So H is 60 meters. So this one is 60 meters, right? Okay, I just show all the result here. Okay, and then now you have to calculate what is the sec, the S1 and also S2. As we know that this is the case that is not equal, the tower is not equal level, so we have to use this equation. Okay, S1 and S2. Okay, so we know that from here, this is the equation. From here, we know that H equivalent to S2 minus S1. So we just add this formula in this equation. Alright. So, and then you'll get the next equation. And then last, you'll get here x2 minus x1 is equivalent to 256 meters. Okay, this is the second equation. Okay, x2 minus x1 equivalent to 256 meters, right? And then you solve the first equation and the second equation, you'll get x1. Okay, then you'll get x1 is 122 meters and x2 you got 378 meters. Okay, from here you can use this value inside this formula and then you'll get the S1. Okay, here is 7 meters. Okay, so in order you to calculate what is the height or the clearance of the lowest point 0 from water level, which is H1, you have to calculate the height of the tower, which is 30 meters. You have to minus with the sec 1, S1, 7, right? Then you can get the height, the H1. So H1 is equivalent to 30 minus 7. They'll get 23 meters. Okay, the next question is you have to find what is the clearance midway between the support. So as we know that P is the midways, so we can conclude that from here to here is 250 meters, and here to here is 250 meters, right? Okay, so we know what is x1. We have to find x because of what? In order we want to get what is H2, we have to find what is the S mid. Okay, the set of the midpoint. Okay, so this S mid, we need to know what is the value of x. That's why x equivalent to length here 250. You have to 250. You have to minus with x1, which is this one is 122 meters. Ni lah, this one lah. Alright, so you can get x is 128 meters here. This one. This one, alright. After that, you get the x, then you can calculate what is the S mid. Okay. Okay. We'll calculate what is the S mid. So S mid here is, you use this equation, Wx squared divided by 2t. So x is this one. Okay, from the point of 0, and then you'll get 7.68 meters for the 7.68 meters, alright. Then after that, you can get what is the clearance of the midpoint P from water level, which is H2. This one lah, H2. So H2 is, you have to calculate H plus S mid in order to get H2. H2 is H1, okay? H1 plus S mid. Okay? H1 is 23, and then S mid is 7.68, then you get 30.68 meters for the H2, which is the clearance of midpoint P from water level. Alright. Okay, next is the mechanical properties. Okay, mechanical factors of safety to be used in transmission line design should depend to some extent on the importance of continuity of operation in the line under consideration. Okay, in general, the strength of the line should be such as to provide against the worst probable weather conditions. Okay, now we will discuss some important points in the mechanical design of overhead transmission lines. Okay, so the first one is the tower height, right? So the tower height depends upon the length of the span. Okay, with long spans, relatively few towers are required, but they must be tall and costly. It is not usually possible to determine the tower height and span length on the basis of direct construction costs, because the lightning hazards increase greatly as the height of the conductor is increased. Alright. Okay, next is the conductor clearance to ground. The conductor clearance to ground at the time of greater sag should not be less than some specified distance, okay, usually between 6 and 12 meters, depending on the voltage, on the nature of the country, and on the local laws. Okay, and then sag and tension. Okay, when laying overhead transmission line, it is necessary to allow a reasonable factor of safety in respect of the tension to which the conductor is subjected. Okay, the tension is governed by the effects of the wind, ice loading, and temperature variations. So the relationship between tension and sag is depend on the loading condition and also the temperature variation. Okay, for example, the tension increase. Okay, the tension increase when the temperature decreases and there is a corresponding decrease in the sags. So tension increase, okay, temperature will decrease and sag will decrease. Okay. Okay, and then we go for the conductor spacing. Spacing of the conductors should be able to provide safety against flashover when the wires are swinging in the wind. Okay, the proper spacing is a function of span length, voltage, and also weather conditions. Okay, the use of horizontal spacing eliminates the danger caused by unequal ice loading. Small wires or wires of light material are subjected to more swinging by the wind than heavy conductors. Therefore, light wires should be given greater spacings. Okay. Okay, and then conductor vibration. Wind exerts pressure on the exposed surface of the conductor. So if the wind velocity is small, the swinging of conductors is harmless, provided the clearance is sufficiently large so that conductors do not approach within the sparking distance of each other. And finally is the stringing charts. So for use in the fieldwork of stringing, the conductor's temperature sag and temperature tension charts are plotted for the given conductor and loading conditions. Okay, such curves are called stringing charts. Okay, this figure shows the stringing charts. Okay, this chart is very useful while stringing overhead lines. Okay, for example, when hot sunny day, the temperature will be increased, right? Okay, when the temperature is increased, therefore the tension will be decreased and hence the sag will be increased. Okay, however, okay, so when cool day, the temperature will be decreased, alright, the tension will increase and the sag will decrease. Okay, that's all for chapter 4. Thank you so much and we'll continue for chapter 5. Assalamualaikum warahmatullahi wabarakatuh.